We're told computers use ones and zeros, but electricity doesn't know what a 1 is. It only knows on and off. In this video, we're going to visualize exactly how we use raw electricity to create logic, one transistor at a time. So firstly, what even are transistors? Transistors are semiconductor devices that act as electronic switches. They can also amplify signals, but we won't discuss that today. There are many types of transistors, but fundamentally they all do the same job. They just work slightly different internally. Computers mainly use MOSFET transistors, which have this symbol. However, for simplicity, we'll use the symbol of an NPN bipolar junction transistor. BJTs aren't really used in modern computers due to a few factors we won't get into, but functionally, they behave in a very similar way. Transistors have 3 pins: the collector, the base, and the emitter, which acts as the output. When a small signal is applied to the base pin, the transistor turns on, allowing current to flow from the collector to the emitter. But without current to the base pin, current won't be able to pass through. Now that we understand how a transistor works, we can place it in a simple circuit like this. The transistor's collector is connected to the power supply, meaning voltage is available there whenever the device is on. If the input is 0, the transistor stays off, so current cannot flow through it, and the output stays at 1. If the input is 1, the transistor turns on, allowing current to flow through it, and since the transistor has little to no resistance with a direct path to ground, it is a more desirable path, so current will flow through the transistor and the output will be 0. Since the output is always the opposite of the input, this circuit is called a NOT gate. Now, a single NOT gate is cool, but it can't do much. To build a CPU, we need gates that can compare 2 different signals. This is where the AND gate comes in. An AND gate requires both inputs to be 1 for it to output 1. But if any or both inputs are 0, it'll output 0. To build this with transistors, we simply put them in series, one after the other. If we only turn on transistor A, the current gets stuck at transistor B. If we only turn on transistor B, current gets stuck at transistor A. The only way to get a 1 at the end is if input A and input B are both active. Okay, that's great. But if we want a 1 when either input is active, we use an OR gate. We just place the transistors in parallel instead. Now the current has 2 separate paths to the output. As long as at least one path is open, the signal gets through. Now that we've seen how transistors build our basic NOT, AND, and OR gates, we need to look at a few more gates. First up is the NAND gate. To build this, we take our AND gate, and we flip its behavior by adding a NOT gate after it. A NAND gate outputs 1 at all times, unless both inputs are active. Great! Now if we replace this with an OR gate, we have our NOR gate. NOR gates output 1 only when both inputs are 0. We've covered the basic logic gates. But to move from simple logic to actual computation, we need one more specific behavior: the XOR gate. A standard OR gate is satisfied as long as at least one input is active. It doesn't care if both are. The XOR, however, is a bit more specific. It only outputs a 1 if the inputs are different. If you have a 0 and a 1, it fires. But if both inputs are 1, the gate outputs nothing. To create the XOR gate, we can arrange our logic gates like so. Perfect. This was the final tool in our kit, and the one that finally allows our transistors to do incredible things together. Looking at these 6 symbols, it's hard to imagine they're responsible for everything you see on a digital display. But a modern processor doesn't use anything smarter than these, it just uses billions of them. By combining these simple yes and no decisions at incredible speeds, we go from shifting electrons to powering the modern world. We've turned raw electricity into pure logic, and that is the true power of the transistor.